All right, welcome to your multi-level modeling lesson. There's a couple different ways to think about multi-level modeling. One commonly recommended way is to start with random effects ANOVA and build from there. So we're going to do that first, and I'm going to review. I'm assuming, maybe I shouldn't assume anything, but I'm assuming that you may have seen random effects ANOVA in the past, let's say in your univariate stats class. But again, I'm not assuming much. So I'm going to review that first and what this random effect concept is, because that random effect concept will then lead us to multiple levels to fulfill our multi-level modeling. So a fixed effect is something that we've seen in almost every ANOVA that we've ever done, and that is an IV whose levels are purposefully chosen. Often you have an IV with levels that have been manipulated, or you're even in a correlational study, let's say you are comparing levels of an IV by your hypothesis. A random effect, however, is something where levels are randomly chosen, which seems kind of strange. Why would you randomly choose, let's say if you're manipulating an independent variable, why would you randomly choose the levels? Well, there's some context here that helps. And so the first example here is, let's say you're trying to select different times throughout the day. So you have instead of 8 a.m., 12 noon, and 4 p.m. as a purposefully chosen fixed effects IV, you have randomly selected times that came out like so, 9:37, 11:14, etc. That would be one use of a random effects design, because let's say you're just trying to get at somebody's mood throughout the day, and a random selection is helpful because let's say you're trying to assess the mood regardless of time of day, something like that. But you can already tell if it's regardless of time of day that your hypothesis is looking a little bit different than, let's say, comparing morning, afternoon, and evening, and you're purposefully choosing those three times. So there might be some utility to the random effect. The most common use, however, is a nested design. So we have an example that I'm going to come back to here in a little bit for the multi-level modeling data analysis, and that is I selected some ratings of professors on ratemyprofessor.com, and I actually compiled this data. And then you can compare across schools and across different individual variables within the schools. So for example, here we have 5 professors at CSUN, 5 professors at UCLA. Actually, I think I'm going to use 6 each, but that's okay. And then we're going to have some other schools in there. And professors are nested within universities, such that each professor is not teaching at multiple universities. At least that's what's assumed for this design. So there's a professor at CSUN, that professor is not at UCLA, and so on. And so you can imagine if you ignore the school variable, you could look at things like, well, if the professor is just being rated as easier, then that means that they're going to be rated better overall. That could be a hypothesis regardless of school. But then you could break it down into school, add that school level, or nest your professors within their schools, and you could say, well, at UCLA, the easier the professor, the more popular they are. But at CSUN, the same is not true. Something like that. So that's what we're looking at in terms of multi-level modeling. For ANOVA, we're just acknowledging this nesting component, or this random effect. It's a special case of random effects, such that the IV now professor is random. That's what it's denoted as. And then we move forward from there with some sums of squares and some familiar-looking ANOVA calculations. So we could declare any variable, any IV, as random or fixed. So we could look at a one-way design as either a fixed, between, or within. That's what we've usually, fixed between would be just like a regular independent samples ANOVA. Fixed within would be regular dependent samples ANOVA or repeated measures. But you could declare a between subjects IV is random, or within subjects IV is random, and analyze accordingly. So we're going to do category number 3 here in a minute. That is the random effects between groups ANOVA, or between subjects. And then you have all these different combinations. If you look in the middle here, you could have it's another way of having a mixed design, because you could have one IV that's fixed and one IV that's random. So you could have a mixed design where you have one of each, and then you could also have one between subjects and one within subjects IV, which is already a mixed design. So it's like a doubly mixed design, or they call it mixed, fixed, random, mixed ANOVA or something like that. But in between here, when these are with the two IV designs, you have at the top you have the between, within, and mixed ANOVAs, regular ANOVAs, and at the bottom you have the full random effects two-way ANOVAs with both IVs as random effects. So the middle ones are the mixed ones, and we're not going to get into two-way random effects ANOVAs here. We're just going to stick with the one-way as an example. And again, the main point of this is to get you to multi-level modeling and concept. And so let's take a look at this independent samples or between subjects random effects example here. So if you're on YouTube here, which I'm sure you are, you probably cannot see this. I'm not going to go over this example here in this video, but this is from Tabachnick and Fidell's ANOVA book that you may have used for your univariate stats class. And this is just it's on page 631, and it's a nested ANOVA or random effects ANOVA one-way example. And so you can use this for your notes when you're doing your homework. This is, you're going to get a sum of squares for A, which is your half day versus full day variable, and this is an example based on skiing. So you have like skiers who either skied a half day or a full day. And then you have within that two groups. So maybe those two groups had different instructors or something like that. So, but these groups are nested within half day and full day. So you have group 1 that got only a half day instruction, group 2 that also only got a half day instruction, group 3 full day, and group 4 full day. And since they just don't cross over, so like group 1 did not get full day, they only got half day, then that means that group 1 is nested within the half day category. So you have sum of squares for A, which is half day versus full day. Then you have sum of squares for B, which is your grouping variable, but you have to go B/A because, well, group is nested within half day or full day, and so that slash represents nesting. And then when you get your error term here, it's S/B/A, and that is for subjects nested within groups nested within a half day or full day. So, those are your three terms: A, B/A, and S/B/A. And you just got to make sure that you remember which to divide by which. And so I'll show you what this looks like in SPSS here in a minute. The error term for A is B, or B/A, that is. And then the error term for B/A is the other one, S/B/A. So when you're dividing, you're going to get mean squares for each, and then you're going to divide accordingly. And here's your effect size calculation. So the intra-class correlation denoted with this, looks like a P, but it's actually a Greek letter rho. This is going to come into play for multi-level modeling in a minute as well. And this is just the effect size for each effect. So that first formula there is for A, in this case half day versus full day. And then the second one is for B, which is the groups. And so you can see the error terms shake out there. The B/A is the error term for A, and then the S/B/A is the error term for B/A. Lots of subscripts. Okay, so let me show you what this looks like in SPSS. All right, so this is your data in SPSS. You've got, like I said, half day and full day. That's your length variable here, denoted as 1 is half day and 2 is full day. And then you've got group. Group is nested, so you've got 1, 1, 1, 2, 2, 2. You see that? So it's like these first three people were in group 1, and they've got only half day. And then they've got the dependent variable, by the way, is skiing speed. So you've got 7, 6, and 10 as the speed for those three people. And then for 4 through 6 here, they're also half day, but they were in group 2, and so on. The key here is to not call group 3, 3, and group 4, 4. You then repeat and go 1, 1, 1, 2, 2, 2. And this helps SPSS kind of organize the data as a random effects design, as we'll see here. So the way I'm going to do it is I'm going to go partly through the point and click, then I'm going to paste at a certain point, and then we're going to do the rest through syntax. That's the the method that I have used in the past to get my way through a random effects ANOVA. There may be other ways. In fact, you can use a syntax, a complete syntax if you'd like, to get yourself through it. But I like to at least do a little bit point and click if I can, if it makes sense, if it helps me out. So we're going to go to Analyze, General Linear Model, and Univariate. And we're going to put speed over to dependent variable. We're going to put group over to random factor. And then we're going to leave length where it is for now. And we're going to click Paste. And again, this gets us most of the syntax that we need, but it's going to leave out a couple things. So we need to type those things in. So we're going to just put length in a couple locations here. So length goes in next to group in the second line of code here under uni ANOVA. So it should say speed by group and length is what's added in. Then you can leave the rest of the lines the same until the end. And then you're going to add in length here twice. You're going to go length after the equal sign with a space, and then group, and then no space, and then parentheses length to distinguish the fact that the groups are nested within length. So whatever is nested goes first, and then whatever is the nesting variable, in this case length, goes in the parentheses. So the nesting variable was length. We left that out. That's half day, full day, and then we typed it in here as well. So now we're good to go. So we can go ahead and highlight this and click the play button to run. And we're going to get some output. And you can match this up to the Tabachnick and Fidell example there. Tabachnick and Fidell actually had a couple of typos in there, which I later confirmed were indeed typos by doing the math. They weren't major typos, but anyway, your test of between subjects effects is going to have your key information. So the 33.33, that's your sum of squares for A, which in this case is half day versus full day. The F there is 50.0. In the Tabachnick Fidell book, it's 49.75. Really threw me off. But anyway, this I later confirmed is correct. The p-value 0.019, so we do have a significant effect of full day versus half day training. Presumably the half day people are, well, is it true? Yes, the half day people seem to be averaging a higher number on speed. So if you only are trained for a half day, you're actually going faster. Maybe that means that you're out of control and you're flying down the mountain and crashing. I don't know. Anyway, so that's the 0.019 there, significant value for length, which is half day versus full day. Then you have the other variable here, which is B/A in the textbook example. B/A, B is the groups, so there is no significant effect of group as evidenced by this 0.751 p-value. 0.296 is your F value. In Tabachnick and Fidell's example, it is 0.30, so I guess they may have just rounded on that one. In fact, maybe they rounded on both. Well, no, they didn't. Anyway, so those are your effects that you need. The error term down here is 18, and so that's going to be right here. The sum of this is your S/B/A sum of squares, 18. Your degrees of freedom are in there as well. You can see, and the 2.25 is the mean square for that error term. So anyway, you can match that up, like I said, to the textbook. The other thing to note here is the interclass correlation calculation, which I will let you apply from the notes here. The notes have it as the mean square for A minus the mean square for B/A, and so on. So for this particular example, you can fill in the mean squares accordingly and then divide. And by the way, the N in this case is number of people per group. So in our example, it's 3 because we have 3 people in each group. Okay, on to multi-level modeling. So we can think of multi-level modeling as a regression approach to these random effects or nested designs. We can also think of multi-level models as regression. It's a regression framework, and we can, let's say, have 10 different regression equations. And if we have 10 different regression equations, we're going to have 10 different intercepts and 10 different slopes, and then we can start comparing intercepts to each other and slopes to each other, and that's the sort of the end result of what you're going have with a multi-level model analysis. So the example here that we will come back to actually at the end of this this lesson is professor rating and comparing professor ratings at the different schools. So like if you have a level 1 professor that is nested within a university, level 1 is the professor, level 2 is the university, assuming that a single professor is not at multiple universities. And so then the independent variable, in this case professor, is random. And we can look at hypotheses at the different schools uniquely and then compare them across. So for instance, here we have a student's achievement in the class as maybe a possible predictor of how well they enjoy the class or how highly they rate the professor. So student achievement is a level 1 predictor. We can make this hypothesis at any school. And in fact, we could collapse all schools together for this hypothesis. But once you start accounting for school, you might say, well, a student's achievement in the class might be important in predicting his or her rating of the professor at UCLA, let's say, but not at CSUN or vice versa. And so it adds a layer, it adds a level to your hypothesis such that you could come up with something like this. Does professor rating vary with university? Okay, so first of all, are professors just more popular at CSUN overall than at UCLA? We could ask that question. Then we start with that. Then you say after adjusting for student achievement, so maybe professors are more popular at CSUN, but only when the students are doing well in the class. And then also adjusting for differences in the relationship between student achievement and university. So that's a mouthful. We're going to come back to this example and fill in the gaps here as we go. So we can kind of come back to this at the end of this lesson. Meanwhile, we're going to turn to Tabachnick and Fidell's example, and that is the one with ski run times. And if you've looked at this, maybe you have, maybe probably haven't. It's in the multivariate statistics textbook, the multi-level modeling chapter. And the nesting here is the ski runs, or the skiers, that is, are nested within 10 different ski runs. So you have, presumably you can make hypotheses about how fast skiers will go on run 1, and then that might look a little bit different on run 2. These different ski runs might have different characteristics. So we can add in predictor variables, for example, a skier's skill level. That might be really important, let's say, in predicting your speed or his speed on a really steep run, a difficult run, but not, let's say, on an easier one. First of all, we make this prediction perhaps across all runs that a skier's skill level will predict speed of skiing. That is, maybe if you're more skilled, you're going to be going faster. We can make that prediction ignoring which ski run you're on. That's a level 1 predictor in that the second level has not yet been added. But then we transition to this multi-level modeling hypothesis that adds in the ski run. So does speed of skiing vary with ski run? First of all, does ski run matter? If it doesn't, then maybe we shouldn't even continue, but we'll go ahead and run that as part of the steps here of getting a full multi-level model tested. So do the ski runs differ in terms of the speed, average speed that the skiers are flying down the hill? And then we're going to adjust for skier skill levels. That's what we were just talking about. And also differences in the relationship between skill and speed among the runs. So like I said, maybe skier's speed will be faster on the more steep runs, but also maybe skill level matters more on some of the runs versus the others. Maybe skill level matters more on those difficult runs. So the magic of multi-level modeling, we can test all this. And I'm gonna give you a subset of the data here. Tabachnick and Fidell don't actually, I don't think, print their entire data set in the chapter, so we're not going to analyze it. We're going to jump back to the professor and university example at the end here to actually analyze some data, but that will provide you with 2 examples here in this lesson instead of just one. So the first one here is the skiing example. We have run 7472, and then there's 10 different runs, with each of these has sort of like a barcode or a number code there to designate it. So we have a random sample of skiers from that particular run. Skill level is 0, 1, 2. We have just a bunch of zeros and ones here, 2 zeros, 2 ones to start, and then speed is either 5 or 6, and the higher the number for speed, the faster the skier went, and presumably was more successful. Skill deviation I just included there to suggest that when you're adding in a predictor like that, you might be taking a z-score of it, a standardized score of skill. In this case, for skill level 1 is negative 0.39, skill level 0 is negative 1.39, and then the skill level 2, which you don't see there, will be positive on the positive end. So we're standardizing a 0, 1, 2 variable, basically. But you guys don't need to worry about that. It all shakes out as you see here in regression equations. So these are the 10 ski runs, and each one has their own unique sample size and their own unique regression equation. So you see, for example, that first run there, the intercept is 5.47 and the slope is negative 0.31, and that's a unique regression equation for the first ski run. And then you go down to ski run number 2, 7, 8, 2, 9, and it's got its own characteristics. Looks actually very similar, right? But then if you just look down, you see that the intercepts vary. The fourth run on the list has the lowest intercept, suggesting that what is an intercept? An intercept is the value of y, the predicted value of y, when the independent variable x is 0, right? That's what the intercept suggests in a 1 IV regression. So when a skier's skill level is 0, the value of speed here, the predicted speed of that skier is going to be lowest on the fourth ski run and highest on, it looks like, about the seventh ski run. 62821 is the number there. So there's some variance in the intercepts. You can start comparing them to each other. Same thing with the slopes. You see that sometimes, so skill level is our IV. You see that sometimes skill level is, as skill level increases, speed increases. And then for other runs, as skill level increases, like number 3, or number 1, for example, the first ski run, as skill level increases, speed actually decreases a little bit. So that's the first suggestion, that the relationship between skill and speed, IV and DV, depends on which ski run you're on, suggesting that a multi-level model is appropriate, because taking into account which run you're on is it appears to be important. Okay, so moving forward to show you the equations here. So this is that first ski run. There's your slope negative 0.31 and your intercept 5.47, where, as I said, the IV is skiing skill level and the DV is speed. There's your standardized version with the negative 0.45 to represent your beta. So to run this, you would actually just select cases in SPSS and just as you'll see here at the end with the example that I provide you, you just restrict your data to just the skiers who went down that particular ski run, and run a regular regression. And then you restrict your sample to the next one, and you run the next one, run the next regression. So that's how you're going to get your 10 regression equations here. Just select cases, select those specific skiers in this case, and run your regression. So you're going to load them into these regression equations. You'll have, for this one, you would have 10 of them. And then we address our hypothesis piece by piece. So the first one is, does speed of skiing vary with ski run? And I said originally that this first P, if this is not significant, there's no relationship here, it kind of implies that, well, ski run doesn't matter. And so maybe our multi-level modeling hypothesis should not be run as a multi-level model. Maybe ski run, you can just collapse across all 10 ski runs and go from there. But there's no strict criteria on that I have seen. So we're just going to go ahead and proceed regardless of the answer to this particular question. This is called the intercept-only model. The intercept-only model excludes the second part there where we look at the slope as well. So if we're just looking at does speed of skiing vary with ski run, we could just calculate a mean for skiing speed across the 10 runs and then look and see if those means vary. More precisely here, what we're going to do is look at the intercepts. So you got these 10 intercepts. I mentioned some of them are higher than others. And the lowest intercept 3.93, highest one 6.44. So what we're going to do is we're going to try to figure out if those intercepts are varying substantially. And if they are, we're going to conclude that speed of skiing does indeed vary with ski run. So this is what that looks like. We've got some letters and Greek letters and subscripts here. I usually try to keep these to a minimum, but I wanted to show you what this looks like in equation form, and then I'll plug in the numbers as we go as quickly as I possibly can. So in this case, I is the individual within a group. So each group is J. The individuals within the group are I for the subscripts, and so that Yij is person, let's say it's 1, 1, it would be person number 1 in group number 1. And in this case, group is ski run. And the skiers are nested within the ski runs. So the beta 0 with the J is the beta 0, that's the intercept. Beta 0 is how an intercept is now denoted instead of an A or an alpha. We now have a beta 0 in our multi-level model terminology, our labels. And then the J refers to the group. So we're just dealing with the first ski run here, this equation, and then the second one, and then the third one, and so on. And then the E is the deviation of that particular individual. So if we're going to write this out for, let's say, for a skier that went down the first run, we're going to plug in 5.47 because that was the group intercept. And then we're going to see how much that first individual in that group varies around 5.47. And I put in 7.472. That's the label, the group label, or the ski run label. And so you can plug that into the subscript as well. And then we add in this this level 2. So this level 2 is like we have a mean of, so we have 10 intercepts, right, for the different ski runs. We're going to have, you can get a mean of those 10 values. That becomes gamma, and that gamma is the mean. It's like, uh-oh, here comes another Greek letter. Okay, so the gamma is the mean, just the mean of those 10 values. In this case, 10 ski run intercepts, and so the mean of those 10 values. And then we can check to see, this is the next level, because we're not just looking at an individual regression equation, we're looking and comparing regression equations across each other. So that U with the 0 and the J in the bottom, the 0, so the J is the group, the individual group, and this is the deviation of that group from the mean of the group intercepts. So from the gamma. So how much does that particular group deviate from the mean of the overall intercepts? So the 4.98, where did the 4.98 come from? That was the mean of those 10 intercept values. You could calculate that. And then we can plug that in this case. The mean of all 10 intercepts for the skiing example is 4.98. That's your gamma. And then we're going to model that U with the 0J in the subscript. We're going to see how much those different other groups vary around the 4.98. So we're now doing regression, but we're comparing regression equations to each other, and it's next level stuff, multi-level models. Okay, so to combine level 1 with level 2, we're going to put, so the level 1 equation there is the Y, and that's the middle, the Yij with the beta 0 representing your group intercepts. Then you plug in the beta 0 equation that we just showed you, which is this one, the 4.98. And you plug that into the level 1 equation, and you've got a fancy looking multi-level model equation in the bottom there with the Yij as your predicted value for an individual person. Like, let's say the first person is 1, 1. That would be the first person in group 1, in this case ski run number 1. And then the gamma and the U and the E represent the following. So the gamma, again, was the mean of group intercepts. So if you're looking at it here, the mean of group intercepts, and then the deviation of that group, which is the U, around that mean, the deviation of the group intercept around that mean of intercepts, that's the U, and then the individual variation is the E. So we start with the gamma, which is the overall intercept, the mean of group intercepts across the entire 10 ski runs. Then we try to figure out how much the group varies, that's the U. And then we try to figure out how much the individual person varies, and we have the full picture. So we're adding in, instead of in a regression where you have just, let's say, a single intercept, now we have a mean intercept, and then an intercept specific to that person's group, or a ski run in this case, and then that individual person's deviation from the group. So 2 layers. And you can actually, in this case, go 3 layers and 4 layers, but we won't go there for this particular lesson. So let's break this down. So we got the 4.98. That's your mean of group intercepts. Again, if you're looking at your list of 10 regression equations with 10 intercepts, the 4.98 is just the mean of those 10 intercepts. So you can plug that in, and then we can go back to our hypotheses. So for the intercepts only model, we're wondering if speed of skiing varies with ski runs. So this is your test of whether the intercepts vary significantly around the mean group intercept. So we have that 4.98, that's our gamma, that's our mean of group intercepts. We're trying to figure out if the intercepts vary significantly around that value, and this value, or this statistic is called, that's a tau, T-A-O, and that is a tau 0, representing the variance around the group intercept mean. Okay. So feel free to pause me and take a drink. I'm going to do the same thing, and we're going to go on with our results here. Well, I didn't pause myself. I just paused for a second during the video while it's still rolling. Anyway, sometimes there's a lot of statistics in these videos. I need to take a quick breather. But I'm going to keep going, and I'm not going to cut this part because I feel like I woke you guys up just a little bit with this interlude. Anyway. The tau 0, the variance in, okay, so this is the variance of intercepts, and I'm just rephrasing this. So the variance of group intercepts is the variance in predicted speed when skier skill equals 0. That's what a group intercept is. When skier skill equals 0, that means that your regression equation, the slope, that term cancels out, and all you're left with is the predicted speed when skier skill equals 0. That's your group intercept. So the variance in those group intercepts for each ski run, or each ski run's intercept, around the overall intercept, or overall predicted speed when the skier skill equals 0. So I was just trying to take that tau 0 and put it in terms of what an intercept is and what the example is, in this case the ski runs. So we've got the tau 0. We'll find this in SPSS based on the second example here in a little while, at the end of the video. SPSS will give you 0.31. I'm not giving you the math on how that 0.31 is calculated, but it's essentially the same thing as calculating a variance of those 10 numbers. So you would take, let's say, the 10 intercepts and calculate a variance. That concept there is going to be the same as that tau 0, value 0.31. And then you test to see if that, or SPSS will test to see if that value is significantly different than 0. In this case, it is. And so, yes, speed of skiing varies with ski run, and we have a preliminary indication that the multi-level framework is appropriate and is helpful and necessary in this case, because there are differences across ski runs. But there's more depth to what we can do with this multi-level modeling stuff. So this is the full prediction now, adding in the adjustment for skier skill level and a test for differences in the relationship between skill and speed on the different ski runs. So let's see how this plays out. Now we're looking at slopes. So we've got the beta 1 now. So instead of like A and B or alpha and beta, we have beta 0 and beta 1 to designate intercept and slope. So the beta 1 is your group slope, and the J represents just which group you're in. So the J would be number 1 if you're in group 1. And the X is the individual score on that predictor variable, so that's just the IV that we're working with. The predictor variable is the IV in this case. So if we look back at our chart here, you can scroll back to when we had the 10 regression equations. That first group, the intercept was 5.47, and the slope was negative 0.31. And so we plug those in accordingly. And this is negative 0.31 is now the group slope, beta 1 in this case. And we're plugging this in for ski run 7472, so I put that in the subscript again. And there's your display of that. So the second group would have like 5.49 as the beta 0 and negative 0.29 as the beta 1. And you can kind of see how it plays out that way. This is what it looks like in the textbook. So you can plot these different relationships. Suppose you have a scatter plot of just the first, well, I guess the first group is on the right, and then one of the later groups is on the left there. If you just make a scatter plot of each ski run and then have the superimpose the regression line on top, you can start to see the differences. And so this is sort of the graphical representation of the full multi-level model, because you can graph all 10 regressions, right? And then you can superimpose them on top of each other to get a sense for how they're different on intercept and slope. So for example, in this case, the Aspen Highlands ski run there, 62821, they probably could have just called it ski run number 7. But anyway, you can see that the intercept there on the y-axis is somewhere between 6 and 7. And then for skiing, for the first ski run, 7472, it's a little bit lower than that. It's a little bit below 6. So those that's the representation of the intercepts. And then the slope there on the left is positive. The slope there on the right is negative. So there's a different relationship between skill and speed, right, for these two different ski runs. Again, illustrating how not only are the intercepts different, but also the relationship between skill and speed is different, thus providing further support that we need to look at these runs separately, and a multi-level model is useful. Here is the graph of all 10 ski runs imposed upon each other, superimposed on top of each other. So it looks like 4 of the runs have a negative slope and 6 of the runs have a positive slope. That's what it looks like to me. And then if you look at the y-axis, you can see that the intercepts are also varying between about 3 point something and 6 point something. And we can go back to the list of 10 regression equations to confirm these numbers. But what happens is then you have these 10 regression lines, and you can analyze, like we said, is the relationship between skill and speed, is that slope different significantly across those 10 regression equations? Okay, so here's what it looks like in equation form. This is your beta 0, that's your intercept, and your beta 1, that's your slope. And then you have your gamma, which was the one that we saw before, was gamma 0, 0. That's your mean of the group intercepts. Now we have a mean of group slopes with the gamma 1, 0. And so the first equation there I showed you already, that's looking at the variance of the different intercepts around these different equations. Now we're looking at also the variance of the slopes. And again, if there are differences here, we can conclude that the ski runs are different in some way. The U, again, is a deviation of the group slope from the mean of group slopes. So are those slopes differing significantly, we can ask. And if they are differing significantly, then those U values are going to be pretty large. Okay, so this is 4.98 was your intercept value. We saw that already. We can plug that in again here. That was your mean group intercept, or mean for the 10 ski runs when predicted skill equals 0. That's your intercept description of what an intercept is. And then this is your 0.22. 0.22 is your mean of the group slopes. Now this one is going to have a p-value of 0.09. So let's talk about this. This one you'll get from SPSS as well. 0.22 is the is not significantly different than 0, and thus across all ski runs there's no significant relationship between skiing skill and skiing speed. So this is what this is saying is, well, if we go back to all these ski runs here, if we were to collapse them all together into one regression equation, that regression equation slope would not be significantly different than 0. So if we're looking at all of these together and we're not accounting for ski run, we're not going to get any significant relationship. However, once we break it down, right, we're going to see that some of them are positive, some of them are negative, and maybe individually those slopes will be significantly different than 0. So that's, again, what the multi-level modeling framework allows us to do. But for now, we'll say across all ski runs, the mean was not significantly different than 0, and we'll move forward. We're going to get a new tau 0, 0. This is the same thing we saw before, the variance in intercepts, but it is the variance of intercepts while the individual scores on the predictor variable, or while the predictor variable is now taken into account. So, in words here, we have the predicted speeds when skier skill equals 0, that's your intercepts, and we're looking to measure the variance of those, while adding in an IV. So this is a repeat of the previous tau 0, 0, but now accounting for the IV, which is important. And now we're going to get a new tau 0, 0, 0.63, and we're still concluding that yes, while accounting for skiing skill, speed and speed of skiing varies with ski run. So in the intercepts only model, we already found this. Now we've added in skiing skill. It's almost like we're adding in this. This might remind you of an ANCOVA kind of situation where you're accounting for skiing skill. You're adding in another variable, and you're finding that the original significance remained. Okay, SPSS will also give us the covariance between intercepts and slopes. So this is covariance is an unstandardized correlation. So what this is doing is it's allowing us to look at, as an intercept increases, does a slope increase? Or as an intercept increases, does a slope decrease? And so we could eyeball this from the graph. You could look at the lines that, or the intercepts that are higher, and see if the slopes of those lines are higher or lower than those lines that have a low intercept. We could eyeball that, or we could just look for tau 1, 0 in the SPSS output. So this is, again, the covariance between predicted speed when skier skill equals 0, that's an intercept, and the strength of the relationship. Theoretically, like, suppose a ski run is just really difficult, right? And so you have a lot of high speed going down the hill. That's a high intercept here. And if the strength of the relationship for that particular run is higher as well, what that means is that if you have a really steep slope, you're going to have a lot of high speed, and skill matters more. Versus, let's say, that would be a hypothesis, for example. If you have a low intercept, then maybe everybody's crawling down that hill at a slow speed, and so maybe skiing skill matters less in predicting speed for that run. So you can tell these are kind of nuanced, in-depth kind of conclusions, but nonetheless possibly very useful, and multi-level modeling is seen quite a lot in psychology research these days. So this tau 1, 0 ended up as negative 0.29 for this example with a p-value 0.07, so close to significant, not quite. I put marginally significant and less than 0, so if we do conclude that there is something here, we would say that the greater the predicted speed, or the greater the intercept, the smaller the strength of the relationship, which is kind of opposite to what I was just saying. So if the greater the predicted speed, that means that the intercept is higher. People are flying down the hill a little bit faster on this run. If that's the case, then skiing skill matters less, the smaller the strength of the relationship between skill and speed. So it's a little bit counter to the hypothesis that I put together just now. But what do I know about skiing? What about tau 1, 1? Okay, tau 1, 1 is the variance of group slopes. So we're trying to figure out, so we found that the overall mean slope was 0. But I suggested at that point that, hey, some of these are positive, some of these are negative. Maybe the slopes are different from each other. And so that's what this is testing, the variance of the slopes, or the variance of the relationship between skill and speed around the mean overall slope. And in this case, that came out to be significant. So yes, there were significant differences among the 10 slopes, and thus the strength of the relationship between skill and speed varies. Okay, so another in-depth conclusion for you. One more thing to address, and that is the intra-class correlation. We saw this before for random effects ANOVA. In multi-level modeling, it represents the ratio. It has a nice interpretation. Ratio of variance between groups at the second level, which is ski runs here, to variance within those groups. And this is your official gauge for whether that second level is necessary. So if, let's say, the intra-class correlation comes out to be a high value, then you're like, aha, there is there's a reason for that second level. It's justification. It's kind of like an eta squared in one-way ANOVA. You might have noticed this similarities when you did it for a random effects ANOVA, or when I showed you that equation originally. So like I said, a high value implies that the the grouping level matters. Technically, it's that the assumption of independence of error variance is violated and that the errors are correlated. So in other words, the groups are different from each other. The ski run number 1 is different than ski run number 2, and so errors are correlated within those ski runs. And so then if errors are correlated, if the variance within a ski run is unique, then you're looking at a grouping level that matters. In this case, you should separate these skiers into the different ski run groups and not treat them all the same. So for this example, here's your formula. So you have these numbers already. You're going to take your tau 0, 0, put it on top and bottom, and then you take your EIJ, which is your error term there, 0.77. I'll show you where to find these in SPSS. You're going to get a 0.29 for this example. And so what that means is 29% of the variability in the DV is associated with differences in the group, or in this case, 29% of the variability in skiing speed is associated with differences between ski runs. So you can imagine if this is treated as a percentage of variability, the higher the value, the more important the grouping variable is, the more important the ski run is in this case. If it's down towards 0, then you might just not do the multi-level model at all. And so what do Tabachnick and Fidell recommend? They recommend that, well, you do it both ways. Do a lot of work. And so what you would do is, suppose you did the multi-level model here and you got a really low intra-class correlation. Maybe if you're skeptical of whether you should do it, you run the intra-class correlation first before trying to interpret all the other stuff. And you see if it's a high enough value. And then there's no like strict cutoff, like an intra-class correlation above whatever percent is justification. But the higher the value, the better, and you can kind of treat it like an eta squared, like I mentioned. So closer to 100% is better, closer to 0 is worse. So if you're really close to 0, you're probably going to get the same thing whether you run this as like a overall just one regression equation versus 10 separate ski run equations. If it's the higher the intra-class correlation, the more likely those ski runs are important, and you should run them as 10 separate regressions and compare. The other thing that'll happen as you go through is that suppose you run the 10 separate regressions and you do the multi-level model, and then the results suggest, oh, all the intercepts are the same. Oh, all the slopes are the same. Well, then that's another clue that, well, you just need to collapse them all down into one regression. Okay, so short of a clear criteria here on the intra-class correlation, that's when you should run a multi-level model. And so then that's my advice, and also Tabachnick and Fidell's advice. So we're going to go back to the first example with the subject and university, or the professor ratings in university. And I'm going to show you those in SPSS, and we're going to see where these numbers pop up in that example and also in SPSS. So this is your multi-level modeling SPSS demo. I've got a professor rating and professor easiness example. This is real data that I pulled from ratemyprofessor.com. I just went and took the top 20 professors in alphabetical order from each university and made sure that the ratings corresponded to 5s and 4s. So I guess the maximum here is 5 on professor rating, and the maximum for easiness is also 5. And so we might make a hypothesis, for example, that the easier the professor is rated, the more popular they are, or the higher their overall rating, and that this relationship between easiness and rating might be different across different universities. So we've got 7 universities here. If you are following along in your multi-level modeling homework, you will see 8. I excluded Stanford in this case. We have Harvard, Glendale Community College, Cal State Long Beach, Cal State LA, USC, UCLA, and CSUN. Obviously, CSUN is the best of these 7 schools. But anyway. All right, so a couple things to do before we start the actual multi-level modeling. The first thing is to screen for multicollinearity. Now, easiness is the IV, rating is the DV. So typically we wouldn't need to do a multicollinearity check between the two of them, but given that it's a multi-level model setup where we're going to be comparing slopes and intercepts within and across these variables, we need to double check. So the first thing you need to do is run a correlation between those two variables here. I will let you do that. It's just a straight correlation. If the correlation is above 0.9, we have a problem, or at least we cannot run the multi-level model. Anyway, the other thing we want to do is run our, in this case it would be 7 separate regressions. So you would run like a CSUN regression, and then you'd run a UCLA regression, and you would select cases each time. So the way to do that, you would just go to Data and then Select Cases. Maybe you've done this before. And you would go to If Condition is Satisfied, and click on the If button, and move, in this case you would move University over to the right, and do like equals 1. And that would select CSUN and would ban all other professors, all other schools from being in the sample temporarily. So you would do this, you'd click Continue, you'd click OK, you'd run a regression. Then you'd come back, select cases again, switch the 1 to 2 and for UCLA, and then run it again, and so on, 7 times in this case, because we have 7 schools. And then you get your 7 regression equations, your 7 intercepts, and your 7 slopes. And you could then just, on your own, get the mean intercept and the mean slope and use those for your homework or for your comparison, right? Because what we want to do is get that mean. Let's say we get the mean intercept. We're curious to know if the intercepts vary significantly around that mean. Same thing with the slope. We're curious to know if the slopes will vary significantly around that mean slope. And if so, if there is some variance there in either the intercept and or the slopes, then we know it's our first indication that it is important to account for which university the professor comes from. Okay, so we're going to start out by, so once you have those individual regression equations and the mean slope and intercept values, you can move forward. We're going to start with the intercepts only model. And so I've posted this syntax for you on your Canvas page. If you're following along for your homework, you can just copy, paste, or just run this as it is. In the last line here, it says subject parentheses university. That suggests that there's a nested component here, university. Professors are nested within universities. So anyway, you can highlight this all and run it. Again, this is the intercepts only model, so we're excluding temporarily the easiness variable, or the IV. And so when we run the intercepts only model, we're looking for that first initial tau 00 value. So I'm going to find that here in the skiing example. Okay, so this is the tau 00 we're talking about just for the intercepts only model. We're wondering if in the skiing example, does speed of skiing vary with ski run? In this case, we found that it did, in that the intercept values were varying significantly. For our professor example, we're no longer looking at speed of skiing and ski run. We're looking at professor rating and university. So we're going to get a value for the variance therein. And it's going to be in this estimates of covariance parameters box toward the bottom here. The tau is in the estimate column and the intercept row, so 0.209 in this case. P-value 0.126 suggests that professor ratings do not vary with university, thus officially disproving our theory that CSUN professors are more popular. Oh well. Anyway, I don't know if that's official proof, but anyway, from there we grab our next syntax, which is the full multi-level model, adding in the easiness factor as a potential explanatory variable here, or one that might predict rating either for some schools or all schools. So here is the posted syntax for the full multi-level model. That bottom line looks a little bit different. We also have so we have easiness added in a couple different places. So as long as you don't change your variable name, you should be okay. Easiness is there in the top line, and it's also down there in the bottom line a couple of times, or at least once. Intercept, easiness, and then a vertical line, and then subject or professor still nested within university. So We can highlight this and run it as our full multi-level model, and we will hunt for the results. All right, so I will bounce back and forth a little bit to our notes here on the skiing example. The first thing we looked for here was the mean of group slopes and a significance value associated. In this case, in the skiing example, there was no significant relationship between skill and speed, IV and DV, collapsing across all of our ski runs. So now we're collapsing across all of our universities to try to figure out if easiness and rating are related. And so the value we're looking for here is the 0.372676, and the p-value associated is 0.012. So that 0.012 is less than 0.05, so we would say yes, actually, and it's a positive value as well. So the easier the professor, the more popular. Makes sense. Okay, so that's true for all or across all universities. So the next thing we're going to look for is this sort of this repeat of the tau 0, 0. This is the variance of the intercepts, or in the skiing example, the variance of speed across the different ski runs while accounting for the IV, which is skiing skill. So applying this to the professor example, we're looking now for, again, the variance of the ratings across the different schools, but now accounting for easiness. So does rating, and before we found that it did not, but does rating vary across the different universities while now accounting for how easy the professor is perceived to be. So we're going to go down to the bottom box here. This is your estimates of covariance parameters. This has got a lot of good information in it. The first thing we're looking for is that tau 0, 0. That is under UN11, and in this case is 0.992. So that's UN11 row and estimate column. The p-value here, 0.205, suggests that no, rating does not vary while accounting for professor easiness. So still, we're seeing no differences across schools in ratings, or no significant variance anyway. Okay, so the next thing we're looking for is tau 10. Now, in the skiing example, this was the relationship between predicted speed when skier skill equals 0, that's intercept, and the strength of the relationship between skill and speed, that was slope. So we're looking to see if, as the slope increases, does the intercept increase, or vice versa. In this case, we had a 0.07 p-value, so it was a marginal effect. Applying this to the professor example, we're now looking at intercepts and slopes again. The intercept here is the predicted rating when easiness equals 0, which is kind of strange. That means that the professor was super hard, I guess, if the easiness score was 0. So the relationship between the predicted rating when the professor is super hard and the relationship between easiness and rating. As intercept increases, does slope increase? And so we go back to our SPSS output over here, and we're looking at UN21 now. That's the second row of results here under the intercept section. So row is UN21 for tau 10. And the estimate column, you get a negative 0.18 here in this case, and a 0.316 p-value. So no relationship between intercept and slope for this particular set of regression equations. All right, so what's next? What's next is tau 11. This is your variance of your slopes. So we're looking at the strength of relationship between skiing skill and speed across the different ski runs, and there was a relationship there. So ski run did matter. Here we're looking at the relationship between easiness and professor rating across the different universities. Theoretically, if this is significant, then easiness matters more at certain universities compared to others. So we go back to our SPSS output again. We go to UN22, which is the one remaining row here at the bottom. We have a 0.03285 and a p-value 0.454. So we've got some boring results. Here there is no significant relationship or no significant variance in the slope and the strength of the relationship between easiness and rating. Okay, so just one more thing here. That's the intra-class correlation. We're going to have You just have to be careful to pull the right tau 0, 0 because you got one for the intercepts only model and one for the full model. So we need to go back to our intercepts only model output to find these values. Besides that, you can just plug them in like so. So your tau 0, 0, if you go back to your intercepts only model for the professor example, we scroll back up here, the tau 0, 0 appeared as 0.209. That is in your intercept row and your estimate column. And then that E value, that residual value is just right above it. So in this case, it's 0.926. You plug those in, you get your intra-class correlation, and you can interpret based on that. So that's where I will leave off for your multi-level modeling lesson. That was an introduction, a relatively quick one, to the world of multi-level modeling. You can imagine that there may be more layers you can add in, additional levels if you want, additional predictors, all kinds of stuff you can do. So anyway, this is a pretty common method these days in psychological research. So it's, hopefully you got something out of this video.